Okay, so question number 11, we're given the function p of x equals 16 plus 2x to the fourth power minus 7x to the fifth power. Part A is asking for the leading term. So what you're looking for is the term with the highest degree exponential. So 16 doesn't have any x terms. 2x to the fourth power, possibly, minus 7x to the fifth power. This term has the highest degree or the highest exponent, right? So our leading term is negative 7 to the fifth power. And why do we care about this term? We care about this term because it's our leading term based on this exponent, right? The x raised to the fifth power. This is going to tell us about our end behavior. So when your exponent is an even number, your end behavior of your function, they go in the same direction, okay? When they're even and they're positive, they go up in the same direction. When they're even and negative, they go down in the same direction. And this is for the end behavior of your function. When you have a function and the leading term has an odd exponent, like we do in this case, then when they have end behavior that goes in the opposite direction, goes in this pattern when it's in positive function, and it follows the other pattern in reverse when it's a negative function, okay? And we're going to see this once we graph this function as well, okay? So then part B is asking for the limit of the function p of x as x approaches positive infinity. So what we want to do real quick is we're going to go ahead and graph this function again. Okay, so 16 plus 2x raised to the fourth power plus, oh no, minus 7x raised to the fifth power. I need to type that all over again. Everything stayed as an exponent. Minus 7x raised to the fifth. So now we're going to graph this. We're going to change our window to negative 10, 10, negative 10, 10, and graph. And so I actually want to adjust this window out just a little bit so we can actually see the entire function because it wants to be difficult. So let's change our x values. Let's do that. Negative 10, negative 10. There we go. So now you can see that it's an odd exponential term for our highest degree variable. So this is our leading term. It has a leading negative, and so our end behavior is going to follow this pattern. So as p of x approaches positive infinity, so it's asking us as this function, your x values, as they continue to the positive x values in your domain all the way to infinity, what are these y values doing? Well, these y values are continuing to negative infinity. So that's part B. Part C is asking you, okay, when you're following the function and these x values continue to negative infinity, what is going on with your y values? Well, here your y values are going to a positive infinity. Okay? So next problem. Okay, 12. You're given the function f of x equals 5x plus 5 over 9x minus 4. And then for part A and B, you're asked to evaluate at 10, then evaluate your function at 100, and then evaluate the function as x approaches positive infinity. So part A and B, you can do that directly, right? You can calculate that, f of x, wherein x is 10. I'm just writing that messy. When f of x is 10, you're just going to evaluate the function. So 5 times 10 plus 5 over 9 times 10 minus 4. And once you calculate that, you're going to get 0.640 rounded to the thousands place. Okay. Part B is asking you to evaluate the function at 100. So f at 100 equals 5 times 100 plus 5 divided by 9 times 100 minus 4. Calculate that rounded to the nearest thousands place is 0.564. And then part C is asking to evaluate the limit as your x value is approaching infinity. So an easy way that you can do this is as the limit of x approaches infinity, what happens is the plus 5 and the minus 4, those become so minute, you can just omit those. And we're just going to analyze our two leading terms from the numerator and the denominator. So we're just going to evaluate 5x divided by 9x. And we'll reduce here, which is going to eliminate those x terms. So as the limit of x approaches infinity, we're just going to evaluate 5 divided by 9, and that gives us 0.555, repeating, so that rounds to 0.556. Okay, so that's how you do that problem longhand. Now, if we want to do it in calculator, what we're going to do is go to our y equals, type this in, parentheses, 5x plus 5, close parentheses, divided by parentheses 9x minus 4, close parentheses. Now you're going to hit the, let me think about this real quick, second window. And right here where it says independent, you're going to scroll down here, scroll over to ask, and hit enter. Then you're going to hit second graph. It's going to bring you to this table. It should be clear. And so now we're going to type in the value that this problem is asking us to evaluate the function at, right? So for part A, they wanted us to evaluate f at 10. So we're going to enter 10, and the calculator is going to calculate our y value for us. So there we go, 0.63953 rounded to the thousands place is 0.640. So we do the same thing for part B. Enter 100 so that the function is evaluated at 100, and the calculator will calculate our value for us, our corresponding y value, right? And that's 0.564. Now, when we are evaluating this limit as x approaches infinity, my go-to number is just 1,000,000. So 1, 6, the number 1 and 6 zeros. And we're going to hit enter. And so here you see that we're getting the 0.55 repeating. So that will round to 0.556. And that's how you can also do this problem just on the straight calculator. Okay. So next problem, 13. So again, we're given a function. You can do it longhand, or you can do it the same calculator way. And I'm going to show you guys how to do the calculator, because everybody, again, should be familiar with plugging in your variable value for X and calculating that. So I'm just going to show you guys really quick how to do it in the calculator. So open parentheses, 3x raised to the 4th power minus 6x squared, close parentheses, divide by 14x to the 5th power plus 7, close parentheses. We're going to hit second graph. Here we have our values from our previous problem, right? So we're just going to hit delete, delete, delete. It's gone. And now we'll start evaluating this function for the x values that are given. So part A, they want you to evaluate at -6. So we're just going to type in -6, hit enter. And the value for the function given when evaluated at -6 will give you a y value of -0.034 rounded to the thousandth place. Part B, we're being asked to evaluate at -12. So we type in -12, hit enter, and our y value is -0.018 rounded to the thousandth place. Okay, and the same thing for part C. We're being asked to evaluate the function as the limit approaches -infinity. So I'm going to type -1 million. And this is telling me that this is an infinitesimally small value. So this value is approaching 0. Now, if you're not quite sure, what we can still do is graph this function. And I'm being asked to evaluate this for x values as they approach -infinity, so going this way. So what I want to do is actually reduce my y scale. And so I'm going to go to my y window and change this to a -5 to 5 and hit graph again. And here, if we trace this, you can see that these y values are increasingly small. So they are more and more going, the limit is approaching 0. They don't ever, right, actually get to 0. They just keep getting smaller and smaller and smaller. So the limit as x approaches -infinity is equal to 0. Okay. So next problem. Okay, next problem, 14. We're given the function f of x is equal to 2x squared plus 25 divided by x squared minus 25. Okay, so the first question is to identify the horizontal asymptote. So the way we're going to do that is evaluating our leading terms. So in the numerator and the denominator. So for part A, our leading term in the numerator is 2x squared. Our leading term in the denominator is x squared. Our exponent terms on both of these variables, they're the same. So we're just going to cross those out. So all we're left with is 2, and that is the value of our horizontal asymptote, y equals 2. Okay, the next part, B, we're being asked for any vertical asymptotes. So vertical asymptotes are derived from the denominator. So we're going to take our denominator, x squared minus 25. It's the difference of squares, so we're going to factor that down. to x plus 5, x minus 5. We're going to set those equal to 0 and solve, which will give us x solutions of x equals positive 5 and x being a negative 5. So those are your vertical asymptotes, positive 5, negative 5. Okay, next problem. Okay, here we're using our super zoom in, bring this down so you can keep making this function extra large. Okay. 15 is just a graph. Okay. So part A is asking us to evaluate this function that's represented here for the limit of x as x approaches -3 from the negative side. So that's how you read this, as x approaches -3 from the negative side, okay? So we are following our function to -3 from the negative x part of our domain, and that y value is approaching 1, okay? Part B, we're following the function from the positive side to -3, but from this direction. And where does that y value approach? That y value is also approaching 1 from the positive side of the domain. Okay, so now part C, evaluate the limit of f of x as x approaches -3. Well, since we did the limit as x approaches -3 from the positive domain and the negative domain, and they're equal to each other, they're both equal to 1, then the limit of x as it approaches -3 is also equal to 1. Okay, then part D is actually asking you to evaluate the function at -3 and determine the y value. So here, the function, this is x equals -3. This point is not included because it's an open circle. So at x equals -3, the y value for this function is actually 2, this point, which is included. Okay, so then here, our last part is f continuous at x equals -3? And if not, explain. So it is not continuous. The function is discontinuous at x equals -3 because the limit of f of x as x approaches -3 is not equal to the value at f evaluated at -3. So this limit, right, for parts A, B, and C, they don't equal the actual value of the function at when the function is evaluated at -3. So it's a discontinuous function, and the appropriate answer would be this option, B. C wouldn't be correct because the limit does exist. So this one is saying does not exist. And again, this one is also saying that the limit, since f evaluated at 3 does not exist. That's not a true statement because there is an actual value at that point in space. So the only one that makes sense is option B. Okay, so now we are going to determine when the given function in problem 16 is continuous. So here we're going to evaluate and place our emphasis again on our numerator, where we are not, because our numerator, again, right, like we did in the previous problem, our numerator is going to, our denominator is going to be evaluated to determine our vertical asymptotes. So we're going to do that same process for problem 16. So 16, the function given is x plus 3 over x minus 3, x minus 6. Okay, so the first thing I want to do is make myself a very rough sketch number line. There we go. That's my number line. Now I'm going to take this denominator and I'm going to set my factors equal to 0 so I can get my actual solutions. So in this case, this is going to give me an x equals 3, and this is going to give me an x equals 6. Okay, so now I'm going to graph that on my number line. Very, very rough. That's my negative, that's my positive 3. Here's my 6. So these two values represent my vertical asymptotes. If my x value were ever to equal 3 or 6, that creates a 0 factor in my denominator, which creates an undefined point in space because, again, you cannot divide by 0. So let's finish our number line. So in this direction, we're going negative infinity. This direction, we're going positive infinity. These are my points in space that create vertical asymptotes. So I can approach those values, but I cannot include those values because that will create a discontinuity, okay? So in order to start setting up my domain where my function is continuous, I'm going to use these as my points of reference. So all we're going to do is parentheses sets. This way, this way, this way, this way, and this way, okay? Because we're going to use a parentheses around infinity because you can approach those values but not include those values. So the same thing is going on at 6. I can approach these values, but I can't include them. At 3, I can approach it, but I can't include it. So here, I'm just going to make this into a domain notation, okay? So parentheses, negative infinity to 3, union with 3 to 6, union from 6 to infinity. This is the space where my function is continuous. I can approach negative infinity and everything from negative infinity to 3, but I cannot include 3 or it will create a discontinuity in my function. Okay, next problem. 17. So now okay, so let's move on to question 17. Our function is x squared plus 5x divided by x minus 3 greater than 0. Okay, so we're being asked to express the solution in inequality notation and then also in interval notation when this function is greater than 0. So the first thing we want to do is take our denominator, set that equal to 0, and solve. So that gives us x equals positive 3. And then we will also want to do the same with our numerator. So x squared. So let's factor it, which is going to give us a factor of x equals 0 and x plus 5 equals 0. So solving each of those, our one solution is x equals 0, and the other solution is x equals a negative 5. Okay, so now I'm going to sketch a rough number line, and put my points of interest, negative 5, 0, and positive 3. And I need to decide what the function behavior is between all of these spaces. So we are also going to include negative infinity and positive infinity. So we're going to make our life easy, and we are going to graph these. So open parentheses, x squared plus 5x, close parentheses, divided by x minus 3, close parentheses, graph. There's our function. I should have another space. So I think we need to adjust our window. Let's make this negative 10, 10, negative 10, and 10, and graph again. Zoom out because I'm still not seeing a portion. There we go. There's the other part we needed to see. Okay, so let's narrow our, let me trace this and see what we can get this to. These y values are at about 25. Let's change our window, our y min to a negative 10 and graph that. I'm going to change this just a little bit more. Make this like 30. Okay, so here we can see in this area, let's trace our function. So everything from 3, this point 3 to positive infinity, all of our y values within this area are positive. So greater than 0. From 0 to 3, they were over here on this portion of the graph, and our y values were all negative. So from this part of our domain, 0 to 3, our values were negative. Our y values were negative. Okay, and then let's trace and go further back this way. So everything from -5 and going to negative infinity, those y values are also negative. So from this space, our y values are negative. And then if we keep scrolling to past -5, our y values from -5 to 0, they were all positive. So this part is positive for our y values. And so our function is asking us for inequality notation when this function is greater than 0. So when does that occur? They're greater than 0, so they're positive y values from -5 to 0, and from 3 to positive infinity. So how do we write that as an inequality notation? So here it's -5 is less than x less than 0 for this part of our domain. For this area, because it's from 3 to positive infinity, that's for all x values greater than 3. So for part A, it's -5 less than x less than 0, or x greater than 3. Okay, and so now we're going to just take this inequality notation, and change it into interval notation. So this is just going to be -5 to 0, union 3 to positive infinity, and you're done. Okay, so let's move on to question 18. Okay, so we're given another piecewise function. So f of x equals -3 plus x for x less than -2, and 2 minus x for x greater than or equal to -2. Okay, so that's our constraint. This is our function, this is our constraint. This is our function, this is our constraint. It's an x. Okay, so I'm going to put this in my calculator. I'm going to show you guys how to do that. Okay, and we're also going to do the same thing as before, where we enter our constraint on the domain. Okay, so parentheses, -3 plus x, close parentheses, divide parentheses, the constraint, x, second, test, less than -2, close parentheses, enter, and then the next piecewise, 2 minus x, close parentheses, divided by, open parentheses, x, second, test, greater than or equal to -2, close parentheses. And they're going to graph this. And it's going to be pretty small. So let's go back and change our window to the -10, 10, -10, 10. Enter. Okay, so assuming you typed this in correctly, here is your first piecewise graph. And here, this is a less than inequality, right? So this would have an open circle at the end of your graph. And this one, it's a greater than or equal to, so it's going to have a closed circle at the end of your graph. Okay, so process of elimination, we know that graph A is incorrect and graph D is incorrect. And we know that this, again, we can trace our graphs on our calculator. So there we go. So this is telling us this line is the 2 minus x, and our inequality is greater than or equal to a -2. So this function on our homework software is a function that should have a closed circle at the end. So this was the one that should have a closed circle. If you hit up or down, it'll put you on the other function. There we go. There we are. And so this one, we can see that it's a less than inequality. And so this part is the graph that should have the open circle at the end. So B would be the only appropriate graphical representation of this piecewise function. Okay, and so here, based on the constraint, we can also go to the next part and say where it asks the points of discontinuity is /r. Well, we can see that there's a discontinuity here at x equals -2, right? The function is disjointed, it's discontinuous. Okay, then the next part is find f of x at any points of discontinuity. Well, because this is a function that has the greater than or equal to, we would actually evaluate this function at exactly at -2 to determine the y value. So we can do that by going second, trace, value, -2, enter, and that value is 4. Okay? And then the same thing. The point of discontinuity, it's asking us as the limit of f of x, the limit of f of x as x approaches -2, is there a limit? Well, no, we can see that there's not a limit because this line graph and this line graph are not approaching the same value. So the limit does not exist for this function. Okay, next, we are going to evaluate the graph that's given. Okay, so 19, you're going to want to do the same thing where you zoom in all the way as much as possible. Bring this down. Okay, so A, we're being asked to evaluate when f is evaluated at 2 minus f evaluated at 1, then divide. So what we're going to go do is go over to this function, f evaluated at 2, and then go find your y value, which right here is going to be, let's see, 1, 2, 3, 4, 5, 6, 7. That look right? No. Okay, f1, 2, all the way up. 1, 2, 3, 4, 5. Oh, here, right here, 4. I'm sorry, I can't count today. 1, 2, 3, 4. We're evaluating the function, which is this parabola shape. Okay, so f evaluated at 2 is 4. Here, f evaluated at 1 is 7. Your y values were 2 minus 1, which is going to give us a -3. That's all we're doing, is just evaluating the function. Here, make sure you're reading the instructions. The function that we're evaluating is y equals 8 minus x squared, which is the parabola function. Okay? Then part B is asking us to evaluate f at 1 plus h minus f evaluated at 1 divided by h. So let's work that out together. So our function that we just went over, our function of x is equal to 8 minus x squared. Wherever there is an x squared, we are going to substitute in 1 plus h. So we need to find f of 1 plus h minus f evaluated at 1 divided by h. So I'm going to, wherever there's an x, I'm going to plug in 1 plus h. And remember, for this particular equation, we need to maintain our square term. Okay, so 8 minus 1 plus h squared minus this function evaluated at 1. So that's going to be 8 minus 1 squared, close parentheses, divided by h. So now I'm going to expand all of this, and that's going to give me 8 minus 1 plus 2h plus h squared minus 8 plus 1. Now I need to distribute this negative, and this is still all over h. So 8 minus 1 minus 2h minus h squared minus 8 plus 1 all over h. Here I'm going to combine like terms, which means this 8 is going to cancel this -8, this -1 is going to cancel this +1, and all I'm left with is -2h minus h squared divided by h. I'm going to reduce each of these terms and divide by h. So that's going to leave you with -2 minus h. Okay, so that's part B. Now the same thing for part C. It's asking us to evaluate the limit as h approaches 0 for this function that we're working with. So we've already reduced it to this form. So we just need to evaluate this as h goes to 0. Well, when h goes to 0, this term is just essentially going to disappear, right? So all that we're left with is the -2. So as the limit of this function as h approaches 0 is going to be equal to -2. And that's it. Okay, next question. 20. Okay, this is where you guys are moving into first derivatives. So our original function is s of x equals 4x minus 6. So the only term in this function that has an x is this term, and we can put our kind of invisible 1 there to just keep track. So an easy, if you have a constant value and it doesn't have any x variables on it, then this term is going to be eliminated essentially when you take the first derivative. So we are only going to, for right now, we're going to focus on the terms that have x variables. So we need to find our first derivative. The way we're going to do that is take this number, bring it to the front, and multiply it. So 1, keep everything that's there, keep the 4, and then you're going to take x, 1 minus 1. That is going to leave us with 1 times 4, which is 4, and x raised to the 0 power. And anything that is a variable or a number raised to the 0 power is a 1. So our answer is 4 times 1, which is just equal to 4. Okay, so let's rewrite our first derivative. S prime of x equals 4. And then the next part is asking us s prime evaluated at 1. Well, there aren't any x terms, so there's nothing for us to plug in. So it's just equal to the value 4. The same thing, s prime evaluated at 2. There's no variable term, so that's also equal to 4. S prime evaluated at 3. There's no variable term, so it's still equal to 4. And you're done with this problem. Okay, guys, we're going to take another break right here, and then I believe when we move on to the next section, we're going to do a lot more of our first derivatives, okay? So we'll get some more practice with that.